Good morning, everyone. Really excited to be here with you, talking about this. So the idea is that we want to prove banking transactions on-chain, and how would that look like? Before I start, how many people are familiar with the open banking API? Do you know what open banking is at all? Nice, starting from scratch. Great, so we can trace back this all the way back to the start of the internet. We had internet banking in the early 2000s come in. And then in the 2010s, we started seeing things like GDPR, banking as a service, APIs, everything was starting. Fintech revolution, Venmo, Revolut, the big names. And there was a need to standardize all these APIs. And that's what the open banking API standardization push started moving. 2015, we had a payment service directive in Europe, which is a law that forces banks and institutions to enable this API standard. And things went live around 2020 with open banking APIs. UK, EU, one of the most advanced implementations, but it's implemented in Australia, Brazil, and Hong Kong, South Korea, Japan, and many countries are still adopting it and want to adopt it more. Cool. So why is this interesting? I'll just explain really quickly how the architecture works in open bank in the standard. Just so you don't like. So we have a user that wants to enter that has some fintech application that they're using, and they want to initiate a payment. Maybe like they're paying for some insurance, cool fintech insurance thing, and they instruct their app to contact the bank on their behalf. You do an auth similar to sign in with Google with your bank, and the third-party app calls the bank, and those are the APIs we're talking about. It's the link between the third-party apps and the financial institution. That's where the API standard comes in. And there are two types: account information and payment initiation. We are interested in payment initiation because they're signed, and that's the crux of what we're doing. So, okay, so the really cool part is you have a piece of data that says the status of the payment, who it's going from, who it's going to, and this is signed by the bank, basically, as a first-party signature. And first-party signatures are interesting because they have some legal weight, and they have legal precedence. You can trace it back legally to the person that signed it. And it's the best kind of trust we can have. It's the bank that's saying this bank transaction occurred. Yeah, digital signatures are like a framework in every major country today. So they're very, very they have legal weight all the way. To understand a little bit how the signatures and the root of trust, how do we know these public keys belong to the banks in the first place? So we can think of it as the initial starting point is the law, right? Like the law is what gives the power to any authority to run this root, to become a root certificate authority. So the law is our layer zero, it's L0, starting point. The law gives power to some trust authorities. In the UK, it's one authority, Open Banking Directory. In the EU, we have this IDAS framework for trust services. There's like tens and more than 350 trust providers for different types of things. But we have a certificate authority, and the certificate authority signs to the bank. The certificate's for the bank, and then the bank signs the payment, and that also has a certificate that you can trace. So the root certificate authority, the root is 20 years. The root gives to the issuing certificate authority, which is also part of the trust world. But we have this one has 10 years on it. And then the bank certificate is 1 year. And then we have this server that's called OCSP. I'll come to it in a second, which is like a quick ping service to check if a certificate has been revoked or not. And that it has a duration of 3 days. So how do we actually verify, if we have a signature, the OB proof, open banking proof at the bottom, how do we actually verify this? What do we actually need to do? Whenever we're talking about signatures, there's two things we have to do. First of all, does the signature go back all the way to the root? Do we have a chain of signatures that takes us all the way back to the root? And the second thing we want to check is, has the certificate been revoked? Because the bank could have done something wrong in the meantime, or maybe there was a leak of some sort, and the keys have rotated and they're no longer valid. So traditionally, like we have certificate revocation lists. In a more modern era, we have this OCSP, online certificate status protocol. And yeah, it just tells you if it's good. This is a sample of it over there. It tells you if it's good, when was it produced, till when is it valid, and which URL you can access it on. And the smart contract cannot go into the URL and verify itself. So there is this technique called OCSP stapling, is whoever is proving, go to the server, get this recent signature that says that this has not been revoked, staple it to your application and send it to me, and then I can just verify everything together. So with the OCSP, you're also verifying whether the signature goes to the root, and you're verifying if the timestamp is still good, if the status is good as well. So this is like the main things we need to do to verify an open banking payment. Just a quick summary about the cryptography that's used in open banking APIs. The certificates are X509 certificates, very standard certificate formatting. The signatures are PS256. PS256 is an RSA PSS signature. The formatting is JSON web signatures, very standard stuff. And yeah, the root authorities I spoke a little bit about. And the signature, these are the information that comes with a signature when you decode it, sorry. Yeah, I'll just caveat something. These open banking APIs are permissioned. So you might ask, can I just go now to my bank and call these APIs and get these signatures? No, you can't. We have to go through these third-party apps, and those apps need to be licensed. And to become licensed, you need to do the usual things, like KYC, AML, and these things, which we are going through right now, trying to figure out like what is the best way to bring something like this live so that people can use it. I'll now go to a demo that we did and let Jack explain more about the technical details.
Cool. Yeah, so we'll get more into the specifics. What do we got? Yeah, so I will start with, this is actually live at bolts.money. We're having a little bit of issues with the wallet right now, so if you want to go use it, maybe wait a day or two for a PR to get merged. But this is built, is it going? Yeah. This is built on the Aztec testnet. So basically, this is like a ZK P2P style on-ramp. It's kind of the most simple thing that you could build with open banking. I will skip forward. So first off, this part isn't very interesting. You're basically committing to the bank account that you want to send money to, the currency you want to accept, as well as depositing some tokens in this case, some stable coin. So nothing really interesting is happening here. Obviously, there's a little bit to talk about with like the bank account and currency you're committing to, but yeah, I'm gonna skip over that because it's not cool. The cool part happens when you want to actually on-ramp. Essentially, what you're gonna do is, again, like ZK P2P, you're gonna go onto this app, you'll find a liquidity position that you might want to ramp through. You can see, like, this is Revolut. You haven't sent any transactions yet. But okay, let's go on ramp. So all we want to do is we want to bring 350 pounds on chain. And the UX for this is actually really nice, right? We get to hook straight into Revolut. And you basically just authorize your payment. And right there, that's where we got the signature. So now we've actually acquired a signature over this payload, which we'll talk about in a second. You can see the payment went through moments ago. We've actually done a payment off-chain. Now, on the other side, all we're going to want to do is prove the qualities of the open banking transaction and use that to extract the tokens out of the escrow. And again, this is done not with ZK-TLS, not with ZK email. This is done directly with signatures from a bank. So I'll skip forward again. And there you go. Yeah, you got your money, 350. So that's kind of the flow. It's pretty convenient, and again, the trust assumptions here are very minimal. So we're pretty excited about where that can be applied. But let's actually go into what am I looking for? What's going on? So you saw previously some of the payload, but this is an actual example payload. This is what you would be actually getting from the open banking API. You've got the domestic payment ID. That's just something you would probably use as a nullifier, so you can't replay a transaction. But you really only need three things out of this payload, which are the identification. This is like the blockchain address in an analogy. It's your bank account number as well as the sort code for the bank, at least in the UK, as well as how much you're transacting and what currency you're transacting with. And along with this being signed, this is all we need really to basically link a bank transaction to the execution of a smart contract, again, with the ZK proof. So if you want to see the circuit, there will be more QR codes later, but this is the actual Noir circuit itself. We'll go through it in a second. A little bit about it. It is a library, so like if you want to use it, you can obviously just import into like an Aztec smart contract if you want the privacy layer. But you can also just very easily import it into like an executable and create verifiers for Solidity and Starknet are two that exist currently with NRG4 going on. You're going to see a bunch of new destinations for proofs as well. So that's really nice because, again, you get to leverage kind of the extensibility of Noir and put this in a lot of different places. This circuit is also set up specifically for UK domestic payments, but as we'll look at when we're parsing the JSON, you just have to know what to look for, like what fields you want to extract, and if you wanted to mutate this, it would be very simple. As for the execution itself, it's 250,000 Planck-ish gates, not super meaningful. What is the actual proving time, which is about 4 to 7 seconds on an M1 Mac. And there's also MoPro, if you're familiar, has very recently begun supporting Noir, so I think you would get very similar performance actually out of a mobile app while using this. So. I mean, it's not instant, but it's very fast as far as proving goes. So we'll walk through kind of the three different buckets of logic in the circuit. The first one is we have this JWT payload. We want to actually authenticate that we're allowed to work with it. So we're going to take our JWT and we're going to do something called partial hashing. If you're not familiar, it's just a way to get free gates. Essentially, you partially construct a hash outside of a circuit, and then you finish hashing inside of the circuit. You only include the computation of the hash for the parts of the preimage you want to operate over. So yeah, we're just going to take the preimage, we're going to finish hashing it, and then we're going to verify the PS256 signature over that payload. And once we've done that, we've basically authenticated that whatever JWT we're working with is valid, and we can go on to extract information out of it. Okay, so, and it's a JWT, which means you're going to see like header delineated by a period and then the body, so we need to sanitize it a little bit for the JSON parser. So that's all this, probably could be prettier, but after we've done that, we've basically just got a standard JSON object, and we'll just use the Noir standard library for parsing JSON. So, whoops. So we'll just basically take the entire payload that we've now sanitized, pass it in. This is a little bit of an expensive setup cost to parse this entire JSON object, but once we've done that, selecting out keys and operating over it is very convenient. So now we've got our JSON object, and we can actually operate with it. And then finally, so I guess if really quickly we look, we'll see that like some of these are nested objects. So we might need to traverse through this JSON object, select key to select another key, but essentially we want to get back out these values. And functionally, this is just doing that. It's finding the key for like amount or currency, and then just taking the value. And for amount specifically, also, like if you're doing like the on-ramp, for instance, if you're transacting value, there's going to be a little bit of an extra step of like transforming the ASCII characters into the numerical values. That is in the contracts in this repository, but we don't actually include it in the verification logic directly because there's cases where you might not want to parse that, and it's extra constraints. But you just have to do a little bit of transformation there to actually get a numerical value, and you can do whatever like financial logic you want in a smart contract with that. Okay, so we've proven the validity of an open banking transaction, but like what does that really mean? We've signed it by who? Who signed it? Obviously, outside of a smart contract, there's all this infrastructure for looking up the basically root of trust and verifying stuff. It's pretty straightforward. On-chain, it's a little more involved, right? We need to, in one manner or another, get the root of trust on-chain. So the thing you absolutely have to do is you have to get the root certificate, at least the first one on-chain. And from there, you can kind of build the rest of your registry. You also, I'm not going to dive into the complexities of exactly rotating the root certificates, but at the very least, you want some sort of logic for being able to handle the transitions when they happen, like every decade. So, some sort of cross-signing verification. But okay, we've got our root certificate. We have kind of two approaches that we can go about kind of verifying the chain of certificates, right? And the first way is just to deal with the root certificates, all right? And the reason why this is nice is because there's not like a lot of extra infrastructure we need to consider. We just tell the prover, you're gonna have to go verify the cert chain, and they don't have to worry about like any sort of like service that is responsible for making sure the current registry of like interstitial signing keys is up to date. It can just go get the chain and validate it. The reason why that's undesirable is because you're introducing an extra signature verification as well. Like you're checking the root signature over the signing certificate. Then you need to parse the signing certificate for its public key and then do a second verification. So you're introducing a bunch of proving costs, and that will impede the user experience, right? On the other end, we can just cache essentially or register the signing keys. And this is nice because we get to have the user basically just do one single signature verification. Problem here being though, like what happens if there's a new signing key that appears and that hasn't been registered? You either have to have the user put a transaction in first themselves to add that key, or you need to have some sort of either incentivization or centralized service that is posting these keys as quick as possible. And even then there's still like these edge cases where maybe like someone sneaks in before it's verified and also hurts the UX. So unclear which the best one is. We'll figure that one out, but either of these eventually work. And that's kind of how you would actually establish authenticity on chain. The one caveat here is that these certificates they're not valid just because they exist. They can be revoked, they can expire. And the basic way to check if a certificate is valid or not is a CRL, a certificate revocation list. And this is an example of one. It's pretty small. But you could imagine as time goes on and this CRL gets larger and larger, proving inclusion or exclusion, especially exclusion in a CRL would get prohibitively expensive. So this is where OCSP that Mohammed spoke about comes back into play. We can essentially the same roots authority will have authorized attestations from an OCSP server, which will basically give you timestamps that say this certificate is valid until this date. And you would just basically have to include that with whatever certificate you're using to basically prove it's not revoked. And this is a pretty foolproof way to do that. Okay, how are we doing on time? Okay, so there's some other stuff we could talk about, especially like removing cryptocurrency. Like one of the things that we're very excited about is like basically we can sequence in bank proofs and use these to recognize payments on chain. So I can run through that if there aren't any questions. But if there are any questions, I guess we can do that first. Yeah. So, yeah. So basically what you're going to do is you're going to initiate a bank payment through the open banking API. You saw like in the demo, we went through the Revolut kind of like pop-up modal that initiated a payment, everything went through, and then there was like the white screen that said payment authorized, not very pretty, but they gave us the signature there, and now we have this, we have this with the signature over it. We've already made an off-chain payment before we've even talked about the circuit. The entire off-chain payment has already occurred. What we're doing afterwards is we're taking this, we're doing like a little pre-processing maybe, but we're taking the signature over this as well as this payload. We're authenticating it in the circuit, we're parsing it out, doing all that stuff after we've already gotten the payload, and then also we might go on chain and like, you know, release tokens from an escrow or do some other logic. But basically the entire like off-chain thing happens first and then all of it is retroactive.
So like checking the notification list and checking the certificate, that stuff happens in the circuit or off-chain?
It would happen, well, okay, so part of that is like kind of the split of like how do you want to register this. I'm going to assume that we're just having only the root certificate on chain. Obviously, you would check the certificates before you even initiate a payment, but once you've initiated a payment, you're going to basically take all that certificate data as well, pass it into the circuit and prove it. And this is like, because I guess theoretically you could reveal which bank you're using, but you can, especially if you're using Aztec, it's simple. We're doing this in the Aztec paradigm, but maybe you're on the EVM and you Merkleize like all of the certificates. You would want to obstruct which bank you're using to transact potentially. So you would do all of that in circuit as well. Yep.
Is your project related to ZK-P2P or ZK-TLS?
How much does everyone know about ZK peer-to-peer here? You familiar with it? Okay. It's not related to ZK peer-to-peer at all, but I'll tell you where it's located, where it's connected. ZK peer-to-peer is an on-ramping, off-ramping marketplace, right? Trustless marketplace. What they did initially is they integrated Venmo as a starting point, and then they moved to the TLS approach, and they started integrating Revolut and different ones. But they quickly realized they cannot, like each connector, each bank takes an overhead of doing, to define it on the system. You can think of open banking as like one API that will just onboard UK, EU in one go. So if we are able to use this, one of the first things we could do is just, once we're licensed, is to plug it into ZK peer-to-peer as a form of connector. Because ZK peer-to-peer cannot build connectors for the rest of the world. That's what they realized. So they will just leave that burden to people who really care about their own local off-ramping to build their own connectors. So this could act as a connector. That's kind of the link between them, if you want to think of them conceptually. If there's no question, I'll just finalize by just saying something about, something that we're really excited about is, this idea that actually with this, you don't even need, this whole, like, we thought we were going to ask businesses to go and get a MetaMask and download, figure out how to on-ramp, which is a huge overhead for businesses and even normal people. But with this, there's potentially a path where we don't even have to do that. People can still take part in escrows and smart contracts without the need to go and manage their MetaMask and like figure out how to on-ramp and do these things. So yeah, this is like one of the really cool, exciting features of this that we are excited about, that we want to lean on and explore as much as possible.
Yeah, okay. There are some QR codes. This is just our website. This is the app. This is the code that we showed you. And this is like a pretty extensive write-up on open banking as well as openbanking.nr. if you're interested in following up on that. I guess we forgot to put a Telegram in there. So, do we have? Oh yeah. Yeah, you can also engage with us here if you're interested. We'll be here the entire time as well. So very interested in like exploring open banking and as well all first-party attestations. Right, like IDAS. This is obviously tied to IDAS, but the identity infrastructure as well is very interesting. You know, PDFs that are often signed with IDAS through stuff like DocuSign, actually verifying like the contents of like legal agreements. Yeah, anything that has to do with attestations, trying to make interesting statements about them is kind of what we're looking at, ultimately trying to drive this kind of future where all these things are working together to build more complex proofs. So.
Thank you.